Okay, can you tell me, you guys remember what is Newton's second law? Okay, so F equal to mm. So we will, in this chapter, we'll look at the correct form of Newton's second law. This is the baby version, okay? So we'll look at the next upper level. And also, the other thing we'll do is, see, you've learned how to deal with forces that depend on distance as a function of position. Okay, for instance, you know how to calculate the work done by this force, which was that integral. Okay. So in this chapter, what you want to learn is forces that depend on time. Okay, how to handle those guys. Okay. Can you think of any situations where that arises? Yep.
Like something constantly pulling on something else?
Well, if it's okay, go ahead.
If you play baseball,
Very good. If you kick a football, you play golf, and stuff like that, any sporting event, what happens is, very often in this situation, forces will be zero before the bat comes in contact, and then it'll rise up quite fast, and then go down back again. Okay. In those situations, it turns out that this force, the peak force, when a batter is batting, it can be 3,000 times the weight of the ball. So it went from 0 to 3,000 times the weight of the ball, and came back to 0, all in, depending on how soft the ball is. If the ball is hard, in 50 milliseconds. Okay? In a soccer ball, when you kick the soccer ball, that could last 200 milliseconds and so on, but still quite fast. In these situations, it's impractical to measure this force. Okay? So what we'll do is we'll do the next best thing. What we'll do is, we're experts at calculus, so we know how to calculate this area, and we'll relate this area to what we observe. Okay? All right, so there are a couple of goals. Okay. So we'll give you the real form of Newton's second law. We'll learn how to deal with forces that change with time, and then we'll apply these to collisions and then rockets. Okay, our favorite things. So we'll talk about all of that. Okay. So we'll start off by defining linear momentum, and that's crucial to everything we do, okay, in this chapter. Okay. So linear momentum, it's denoted by P. It's a vector quantity, and it's defined by the mass of the object times its velocity. Okay. So we define another conserved quantity. What does it mean when we say conserved quantity? Yep.
It's independent of package.
Conserved just means it remains, it's not destroyed or created, so it remains constant. So if there was no friction, we said mechanical energy was conserved. Okay. So when I drop this object, its mechanical energy has the same value at every point. That was conserved. If you can account for heat as well, but heat is very hard to measure. So for instance, in this guy, that mechanical energy got converted to heat, except that some of it went here and some of it went there, and that's very hard to keep track of. Yeah. So conserved quantity means it remains constant. So here's where that will come in. Okay. So here's a vector. So let's say when you're playing pool, this ball is going this way and this ball is going that way. You can calculate its momentum, this guy's momentum. You can calculate the total momentum. See, there's the momentum of that guy, there's the momentum of that guy, there's the total momentum. And as long as there's no external force acting on the system, the momentum after collision is the same. Momentum is conserved. So it's a very powerful quantity. Okay. So after collision, this guy went that way, this guy went this way, and look, the total momentum is the same. Yeah. All right, so we define another conserved quantity, linear momentum, which will put an additional constraint on how systems evolve in time. Okay, see, the more constraints you put, the more restricted your motion is. Okay, so now you've learned that your motion has to obey energy conservation, and now we're telling you another thing. It's got to obey momentum conservation as well. Okay, so for instance, after this collision, this guy can't go that way because then momentum wouldn't be conserved. Okay, at that speed. So it tells you if it's going at this speed, this is the direction it has to go at. Yeah. Conservation of momentum is useful for understanding collisions, so we'll be talking about collisions. So the quantity momentum is just as powerful, important, and useful as energy. Okay, the only reason that you don't hear about it more often, it's dealing with a more complicated quantity. It's dealing with a vector. Energy is just a scalar, and you can teach that to young kids as well, adding numbers. Yeah. All right. So linear momentum. So often we encounter situations where the applied force varies with time. Okay, so the force that the bat is exerting on the ball changes with time, and it's changing. For this ball, it's changing over what time span? 50 milliseconds, okay, less than 100 milliseconds. And is non-zero for extremely short intervals. Okay, so we will do a fairly cool experiment where we'll measure this force 500 times a second. That'll be the best experiment you'll do. Okay. So we'll do the impulse momentum theorem. So to analyze such situations, it's convenient to define a quantity called momentum. Okay, so here is linear momentum, mass times velocity. So here is the correct form of Newton's second law. Mr. Newton gave it in this form. What Mr. Newton says is the net force acting on a system is equal to the rate of change of momentum of the system. Okay. All right, let's work this out. Okay, so we'll use the chain rule. It's dm by dt times velocity plus m times dv by dt. What is dv by dt? Mass times acceleration. Okay. So force is dm by dt All right, so every time we told you Newton's second law, we said F equal to ma. Well, what happened to this fellow?
Well, for most things, the mass isn't changing very much.
Very good. So for most things, when you drive from Palm Coast to here, the mass of your car changed less than 1%. You did burn gasoline, and it did change a little. But it changed so little that you can throw this away. When is it that you cannot throw it away? What? I'm sorry?
Short intervals and quick changes.
Rockets. If you're Elon Musk, a rocket is 90% fuel. Okay, in a few minutes, you went from 100 to 5. That's when you can't. Okay? You can't ignore this if you're a squid. You're squirting 10% of your body mass to propel yourself. All right, so there will be situations when you won't be able to ignore this. Okay, but most of the time we are able to ignore this, and that's why we stated it that way. Okay. All right, so here's Newton's second law. Okay, so this gives you, okay, now we're stating some momenta of objects, because here's the deal. So if you know the momentum of an object, this is the change in momentum, okay? And this will tell you what kind of forces you'll need to stop an object in this time, okay? And the shorter the interval in which you stop, the greater the force you'll need. Okay, so for instance, this kind of stuff plays into all kinds of safety devices. If you're going at 80 miles an hour and if the steering wheel stops you, the steering wheel stops you very fast. And that's not pleasant. So what are you going to do for a safety device? You're going to increase this guy. So this guy is smaller. Okay? But actually the airbag does two things. What else does it do?
Spreads out the time.
Very good, my friend. See, airbag increases the time, and not only that, it does the following. See, 10 pounds of this force hurts more than 10 pounds of this force. Okay? So airbags do two things. All right, so this is the momentum, okay? All right, here we go. So there's the airbag. It increases stopping time or stopping distance, and it also, the stopping force is spread over larger areas, okay? So the pressures are smaller, so your skin doesn't break. Okay? All right, so now let's go golfing. So here's the force that the club is exerting on the golf ball. Again, it's zero before the club comes in contact, and it rises up quite fast. And this is somewhere by like 50 to 100 milliseconds, okay? This area under this curve, okay, so here's the force as a function of time. This guy is called the impulse of the force. Okay? Impulse is denoted by I or J depending on the textbook you're using, and what that does is this is the final momentum minus the initial momentum. And we'll show that to you in a second. Okay, mv final minus mv, and now I'm not writing the vector signs. Okay, so if the impulse is in this direction, that's the direction in which the velocity of the object will be. Okay, so now you can see the difference between, let's say, a professional golfer and somebody like me. Okay, their impulse is greater, meaning their final velocity is greater, and the ball goes further. Okay. And not only that, they are able to apply a greater impulse and with consistency. Okay. All right. Okay, so here is the impulse approximation. Okay, so what this says is the following. In many situations, a single force acting for a very short time, so this force acting for a very short time is the predominant force. Okay, what do we mean by that? What are the other forces acting on this system? Okay, there's gravity acting on this system, there's the normal force acting on this system, and there's friction acting on this system. Okay, all these three forces are negligible compared to this force. Okay, so while this guy is talking, we can ignore all these other forces. That's what the impulse approximation is. Okay. In such situations, for this short period of time, all other forces can be ignored. Yeah. All right, so here is Newton's second law. Force is equal to rate of change of momentum. So again, this is the mathematical equation, so we can integrate both sides. We'll integrate, this is the force that depends on time, so we'll integrate this with respect to time, and that'll give us this area. That is called the impulse, so here we use the symbol J for the impulse. Okay. So essentially, you see, F dt is a vector, and you're just adding a whole bunch of vectors and you get a vector. So okay. And again, this is a vector, a small vector, small change in momentum, and then you add a whole bunch. That's the total change in momentum, final momentum minus initial momentum. Okay. Now we'll say, so impulse is the change in momentum. Okay. So now let me drop the vector sign, mv final minus mv initial. Okay. Greater the impulse, greater the change in velocity of the object. Okay. So when somebody kicks a ball further, they've imparted a greater impulse on the ball. Okay. Like I said, oftentimes it's impractical to measure this force. Okay, and we're not even interested in that. Do you want to describe how the speed of the soccer ball is changing over a span of 50 milliseconds while you're kicking it? No, you don't care. What you want to know is what is the speed it comes off of the foot of Messi, you know? And, you know, so we just are interested in the final speed. So oftentimes all we're interested in is the average force exerted. Okay? The average force, so the average force is defined by this rectangle which has the same area as this thing. Okay? So average force times the time over which the force acts gives you the same impulse. Yep. So that's the average force. Okay. Right now we'll talk about conservation of linear momentum. Okay, so Mr. Newton tells us the net force acting on a system is equal to rate of change of momentum of the system. So let's consider this system. Two balls moving, so that's the system. The net force is any internal forces plus external forces. So when they collide, they'll exert internal forces. So when they collide, this guy will exert a force on him. So now let me have them colliding. This guy is exerting force on him, and this guy is exerting a force on him. What does Mr. Newton say about these two guys? These two forces? Very good. Action and reaction are equal and opposite. So the sum of these two forces is 0. Internal forces will always add up to 0. Okay? So this guy is 0. So any net force acting on the system is just an external force acting on the system. And if there's no external force acting on the system, then the momentum will be conserved. So for instance, if you're playing pool, okay, so now I'll draw it sideways. You're playing pool. Well, there is gravity acting on this, but gravity is being canceled by the normal force. So there's no external force acting on the system, assuming there's no friction. And the rolling friction is very small. So when you're playing pool, external force is 0. Okay? So momentum is conserved. The total momentum of the pool balls before they collide is equal to the total momentum of the balls after they collide. Okay? Okay. So here's a very interesting, yeah, so I'll show you this thing. Okay, you ask your question first.
Sure. So
Mm-hmm.
in this example of the pool balls, the pool bars are very rigid, and when they collide, they don't like deform at all.
So-
when we account for that,
So even if they were made of putty, momentum would still be conserved. So what you're referring to is we'll talk about this. That's an elastic collision. In an elastic collision, kinetic energy is conserved. Okay, and if you throw two pizza balls at each other, the momentum still would be conserved. Kinetic energy is not conserved. Okay? So here's an interesting video, hopefully. Okay, so this is a.
Let me show you an extremely reliable way to break an 8 loop. First of all, we want to make sure we get tight track, as tight as possible, no gaps. That's a common mistake from beginners. They get gaps in the rack. We don't want them. Second, we break head on towards the 2 ball, and it should result.
All right, so this is interesting in the following sense. Okay, so what we'll do is when this guy shoots the cue ball, this system, that's the momentum of the cue ball. Okay, the system momentum is the momentum of the cue ball. It hits this million balls, and they go in all different directions until one of the balls hits a side. The momentum of the entire system is the same. It doesn't matter how the break happens, the total momentum is conserved. Okay, so you can, you've seen firecrackers, rockets are shot, they explode, and right after the explosion, the total momentum of all the pieces is equal to the momentum just before the explosion. Okay, yep.
Doesn't that also work with beatings first, though?
I'm sorry?
Doesn't it also work with beatings first, or where it says, what's it third? Not first. Where it says, an object will change, remain still until like actually force hits it. So like, so let's say like momentum will stay the same until it hits.
Yeah, if no force acts on it, its momentum would be the same. That's where we got that law from. Yeah. But here, see, what we're saying is that energy was distributed among a whole bunch of things. See, here's the important thing. Some of that kinetic energy, if the collision is not elastic, some of that energy can be transferred to heat, but momentum will be conserved. Okay? So that was the additional constraint. Okay? So that's a very powerful statement. See, here's the neat thing about the statement. I don't care how the collision happened. I don't care if you put 9 balls in the rack or 100 balls in the rack. Momentum will be conserved, and that's a powerful statement. I don't care how the balls were made. Right? All right, so you guys understand that? Okay, so here's another application in particle physics. You have particles that will decay, break up into other particles. So here's this fellow, a neutral kaon. He'll decay into these are particle-antiparticle pairs. Okay, particle-antiparticle pairs have exactly the same mass and stuff like that. And the thing is, this guy will break up into this, if he's at rest, he'll break up into this particle-antiparticle pairs, and these guys have to move exactly 180 degrees apart. They can move in any direction, but they have to move at exactly the same speed and exactly 180 degrees apart. Why is that?
If they went at any other angle, the velocities wouldn't cancel out. The momentum would not be the same for both particles.
The momentum initially is zero, and the only way the final momentum is zero is if they're moving exactly opposite to each other and exactly at the same speed. So that's the powerful. Okay. So that statement tells you that's constrained that motion. They have to go at exactly the same speed. And now, what other law tells you how to calculate their speed? Energy conservation will tell you how to calculate their speed. So that's what the conservation laws tell you. They tell you these motions are restricted, and you can calculate the parameters. Okay? Okay, now we'll look at collisions. So objects colliding. Okay, so let's say these objects collided, and this was before the collision, then this is after the collision. So if the kinetic energy, total kinetic energy after the collision is equal to the initial kinetic energy before the collision, then it's called an elastic collision. When pool balls collide, they're an elastic collision. When cars collide, that's not an elastic collision. Okay? If final kinetic energy is less than initial kinetic energy, then it's an inelastic collision. Okay? If final kinetic energy is zero, then it's a perfectly inelastic collision. So for instance, you can take two pizza dough balls and hit them at each other, and they'll stop. Okay? That's a perfectly inelastic collision. If the final kinetic energy is greater than initial kinetic energy, then it's an explosion. You added chemical energy turned into mechanical energy. Okay. In all these collisions, so the classification is based on kinetic energy. In all these collisions, what is conserved is momentum. Yep. All right, so I'm looking for the collisions app. Okay, I don't see it. I know it's there. Okay, so notice something. So I'm going to, here the masses are different, and and I'm not going to have a reflecting boundary. And here's one thing you'll notice, that the center of mass, this is the center of mass, we haven't talked about it yet, but the center of mass will maintain constant velocity. Okay. Okay. So this was All right, so I'll show you something that you already knew. But you didn't know. Okay, so you intuitively knew this. Okay, if the two balls have the same mass, and I'll make them collide, and we'll talk about this in a second. When they collide, okay, so this guy went off in this direction, and this guy went off in this direction. If this guy was at rest, initially, the angle between them, do you know what that is?
90 degrees.
Huh?
Looks like 90 degrees.
It looks like 90 degrees. It's exactly 90 degrees. And you knew that because you played pool all the time, and that's what you used to use when you're aiming, trying to make it. So you intuitively knew that, but you didn't know the exact number. Okay? That is true when the collision is elastic and if the two masses are equal. So, if you want to beat the world champion, what do? You take a regular cue ball and you play with it, and when it's his or her turn to play, you put a special cue ball. Anything with a different mass, and they won't be able to shoot anything. All right? So, there is some use to learning physics. That was the point. Okay, so here's the momentum before collision, and here's after collision. Okay, in an elastic collision, in all collisions, what is conserved? Momentum. Okay, and we are just doing classification based on kinetic energy, and kinetic energy is sometimes conserved and not conserved. Okay, so we're using that as the classification tool. So an elastic collision is one where kinetic energy is conserved. And inelastic collision is one where kinetic energy is not conserved. Okay, so here's an inelastic collision in one dimension. Okay, so they're all going in a straight line, and before the collision and after the collision, they're going in the same straight line. Okay, if that is true, then so this is an inelastic collision, they stick together. And if the objects stick together, they're going at a very specific velocity. And this velocity is equal to, the total initial momentum divided by the total mass. Okay, so if they stick together, that is the velocity at which they have to be going. Okay? And we'll do this experiment in lab. Okay? So that was an inelastic collision. What is an inelastic collision? Kinetic energy is not conserved. Now let's do an elastic collision in one dimension where kinetic energy is conserved. Okay. So here is initial momentum. See, this says mass of object 1, velocity of object 1 before the collision, mass of object 2, velocity of object 2 before the collision. So this is initial momentum is equal to final momentum. And since this is an elastic collision, kinetic energy is conserved. Initial kinetic energy is equal to final kinetic energy. Okay. All right. So, and quadratic equations are a pain to solve. So somebody's been nice to you, and it turns out that the information contained in these two equations is the same as in these two equations. So you can do a simplification. This equation is the same as that. So by putting this information in here, you have reduced this equation to this. Okay, let's see, what does this say? V1 initial minus V2 initial. Okay, so what does that mean? So let's see. Let's say this guy is going at 5 meters per second, and this guy is going at 10 meters per second in that direction. So his velocity will be minus 10 meters per second. And 5 minus or minus 10 is 15 meters per second. That's the relative velocity. So if you're going at 5 meters per second and this guy is coming at 10 meters per second, if you're sitting on this guy, he's coming at you at 15 meters per second. Or you're approaching him at 15 meters per second. That's your relative velocity. All right, so you're approaching him at 15 meters per second. And then after the collision, okay, your velocity relative to that guy, you'll be moving at 15 meters per second. That's what it's saying. Okay? So after the collision, your relative velocity is flipped. So it could be that, okay, so you could be going at 8, 7, and then after the collision, you could be 7, and then he'll be going at 8. Okay? So that's what it's saying. Now we'll look at 2D collisions. Okay, so now there are 2 dimensions. Okay, so again, momentum is conserved. Momentum is a vector. So now if it's 2D, 2 dimensions, P final x equal to P initial x, P final y equal to P initial y. Okay. So in this situation, there's only x component of the momenta. So if they collide and go off this way, the y component of the momenta cancel, and these two must add up to that momenta. Okay. So again, x component of the momenta have to be conserved, y component of the momenta has to be conserved. And if it's an elastic collision, then kinetic energy is also conserved. Okay, so your collision has to satisfy these 3 equations. Okay. So the more equations it has to satisfy, the more constrained you are. Okay? Like my mother used to say, you can't spend on this, and that. Where the hell am I to spend the money, right? So, yeah, the more constraints you have, the less freedom you have. All right, this is a good place to stop.